Hello students, welcome to EPG Pathshala. I am Professor B.K. Sen, Chairman, Bibliometrics Expert Committee, Department of Science and Technology, Government of India, New Delhi. Now I am going to discuss about the module on Bradford distribution. The objectives of this particular module is to make you know that how the formulations of Bradford distribution has been given by various bibliometricians, and also the various views on this particular distribution by renowned bibliometricians of the world. Now, Bradford distribution of all the classical laws of bibliometrics has found the maximum utilization or maximum use, and it has also been studied much more compared to other two laws, that is Gibbs law and the Lodka's law. Its use has been found in various areas. It is either for the journal selection in the libraries to find out the core journals in a particular field, or to delete particular journals from a particular field. This particular law, when it is used to rank the journals according to their productivity on a particular field, immediately one comes to know that which are the most productive journal in this field, which journals are medium productive, and which journals are the least productive. So using this, librarians in the world, they are using this law to a great extent, not only for the selection of journals, but also for the deletion of journals. Coley's formulation for Bradford distribution. Once Bradford law became known to the world, then many scientists, they started giving the mathematical formula for the law. The reason being, Bradford did not give any mathematical formula for his distribution. He just gave the definition and ended it. Thereafter, bibliometricians, statisticians, they went through the law, they experimented, and thereafter they came out with various formulations. So we are going to discuss here some of this formulation, and one of the formulations is by Coley, and here we find that is fx is equal to 1 plus b log x, where x is greater than c. Now in this case, fx, cumulative number of papers contained in the x number of most productive journals. Here I will have to explain. We have seen earlier that for verifying the Bradford law, we are to tabulate the data. In the data, we give first the rank, then the periodical, number of periodicals, then the number of articles, then the cumulative number of articles. Now here, that is, the Fx just relates to cumulative number of articles or papers contained in the X number of most productive journals. Now we have to explain the term most productive journals. When we tabulate, or in the tables when we discussed classical laws of bibliometrics, we have seen that in the tables there are certain journals which contain a very large number of papers, then gradually number of papers per journal declines, and ultimately we find a very large number of journals containing only one paper. In this case, he has said that when we are taking the cumulative number of papers, then we are taking those papers only which pertain to most productive journals. Suppose in a table we find that some journals have contributed 100 papers and some 90, some 80 or 50 like that, and then the journals which have contributed 80 papers or more can be taken as the most productive journals. So depending on the data, we are to decide the most productive journals. So here Fx is the cumulative number of papers or articles, X is the number of most productive journals, and C is the number of journals figuring in the nuclear zone. In the previous recording we have seen 10 journals belong to the nuclear zone. So when we draw the Bradford bibliograph, then the Bradford bibliograph shows the nuclear zone, or when we tabulate the data, there we find out the topmost journals which are contributing to 1/3 of the articles. So in the previous case, we have seen that the first 10 journals were contributing 444 articles, that is 1/3 of 1332 articles. So that is the nuclear zone, and that is expressed by the letter C, that is the number of journals in the nuclear zone. And using this formula, for example, Fx is known to us, X is known to us, and C is known to us. So we can find out the value of B. Cole find out the value of B for petroleum literature, which was 0.43. So using this formula, we can find out the value of B for any other specialty. Now, Bradford defined his law, but he did not give the formulation of his law. Thereafter, the bibliometricians like Lime-Queller, Cole, Brooks, and others, they have given the formulation. Of these formulations, the Cole's formulation, Brooks' formulation, they are more or less easy to apply, easy to understand, easy to derive. On the other hand, Lime-Queller's formulation is not that easy, and Brooks opined that the equation that was given by Lime-Queller was a compromise, since Lime-Queller accepted the experimental empirical data as both complete and exact, in reality which is not. In addition, unfortunately, though Lime-Quer's formulation can be used theoretically without difficulty, but it has some disadvantages for the practical documentalist. Lime-Quer's formulation. Like Cole, Lime-Quer also analyzed the published data of Bradford distribution. As we have already pointed out, that Bradford defined his law, but he did not give any formulation. So, Lime-Quer tried with this and gave the formulation where fx is equal to log normal 1 plus beta x divided by log normal 1 plus beta, then 0 is less than x, x is less than 1. Here fx, that is cumulative fraction of the references. Here again, that is, these references are articles. When we compile a bibliography, then we take the articles, and many of these articles appear as references at the end of research papers. So, Lime-Quer, he meant by the term references the articles, and by the letter x, he means corresponding fraction of the most productive journals. We have seen earlier in the Cole's formulation also that he also took the most productive journals, that is the journals which are contributing maximum number of papers. Lime-Quer also did the same thing, and beta is a constant related to the document collection, and this beta is to be determined using a very tedious statistical method which normally is not taught in MLIS classes. So, that is for Lime-Quer's formulation, it was not used for a long time because of this problem and also other problems which we will discuss in our video lectures. However, some bibliometricians, they have made some modifications to the law, to the formulation, and because of the modification, it is being used by some bibliometricians for the verification of Bradford's law. But even there, it has been found out that the number of articles in each zone goes off widely from the number which Bradford had conceived. However, using Lime-Quer's formulation, the bibliometricians get the Bradford multiplier which is more or less equal, but with those multipliers, the number of corresponding articles which we get, they deviate far away from the equal number of articles as was defined by Bradford. We have discussed Bradford bibliograph already. Still, we are discussing it here, since this graph is necessary to derive some values for Brooks formulation. Without this graph, that value cannot be derived. Naranan's viewpoint, we have seen in the case of Bradford distribution that many bibliometricians from all over the world, they have contributed, they have given their views, they have given their comments, they have given their formulations, but there are they are all non-Indians. The only Indian that figures in this is Naranan. Now, what is said in the case of Bradford law is also important. He said, Bradford law of bibliography of scientific literature is explainable in terms of the underlying power law distribution of the number of articles in scientific journals. If the law emerges as a natural consequence of exponential growth of scientific literature and journals at comparable rates, a model like this predicts a strong correlation between the age of a journal and the number of articles it carries. Naranan has talked about the power law distribution. Now you might not be knowing what is this power law distribution. I like to tell you that here the power law is a functional relationship between two quantities. When a relative change in one occurs, there is also a proportional change in the other. For example, you take the area of a square. Now, the moment the side of a square, value of the side of a square increase, the area increases by square. Suppose the value of a side is 1, the area is only 1. But if the moment this value is changed to 2, the area becomes 4. This is the power law. Another thing Naranan said is about the exponential growth. So when the growth is like 1, 2, 3, 4, 5, 6, it is linear growth. But when the growth is like 1, 4, 8, 16, 32, it is called exponential growth. Brooks formulation. Brooks was not happy with the formulation of Lime-Queller. He found out several flaws in the formulation. Hence, he decided to give or to formulate something new for the Bradford law. So he provided two formulations. One is Rn is equal to K log n, where Rn is the cumulative total of relevant papers found in the first n journals. Again, I like to point out that all the formulators of the law, whether Cole, Lime-Queller, Brooks, they did not take the entire set of periodicals or journals. They have taken only a part of it, most productive journals. Now here in this case also, Rn here we find out the cumulative total of relevant papers found in the first n journals. The first journals are usually the most productive journals. Here he just used the word in a different way. N stands for number of journals and K is a constant. So using the formula, we know the value of Rn and also of N. We can find out the value of K without any difficulty. Second formulation of Brooks. It is Rn equal to N log N divided by S, where C is less than or equal to N and N is less than or equal to capital N. So Rn, as in the earlier case, we know that it is the cumulative total of relevant papers found in the first N journals. Capital N is the total number of periodicals expected to publish paper on the subject. Small n, number of journals, is value of n at the intersection of the straight portion of the curve with the x-axis. C, value of n at the point where the straight portion of the curve begins, and for obtaining the value of S and C, it is essential to draw the Bradford bibliograph, and this in the Bradford bibliograph which has been shown to you during the video presentation, there the value of S is 4. So here the bibliograph you will have to, if you are working with this formulation, then the that is the essential thing is that you will have to draw the bibliograph, and from the bibliograph you will have to find out the value of S. Without the bibliograph you will not be able to find out the value of S, and similarly you cannot find out the value of capital N. So from the formulation Rn, N and S, when this becomes known, we can find out the value of capital N, which indicates the total number of periodicals which are expected to publish articles on that particular subject. It is the graph of a power law distribution, which Narayanan has pointed out that Bradford law follows power law distribution, and the shape of the curve is like this, which you have seen in the case of Lothkar's law as well as in the case of Gibbs law, but the curve in the case of Bradford law is not like that, that is J-shaped. Bookstein's viewpoint. Bookstein is also a very important bibliometrician. After going through the distributions of Bradford, Lothka, Giff, as well as Lime-Queller, he found out that more or less they are equivalent. In each case, there is a set of entities. For example, there may be the scientists, there may be words, there may be articles, and like that. And these are producing events like publications, articles, journals, or occurrences, that is frequencies, over some dimension of extension. This may be length of the text, as we see in the case of GIF. It may be time which we take, say it may be in Bradford or Lotka or any other law, because while we are compiling a bibliography, we have to take into account time as well. And in each case, the distribution describes the number of occurrences or events over a fixed interval of that dimension. So this is he wanted to unify all these laws into one. As we have seen, the physicists, they are trying to unify the four forces of nature. Similarly here, Steins also tried to unify these various laws. It deals with Bradford multiplier, about which we have already talked. Bradford found from his data the multiplier is more or less 5, but in many cases we have seen that the multiplier goes above 5 or less 5. Now it has been seen that there is an ambiguity between verbal and graphical formulation of Bradford law. Bradford himself, he just stated the law, defined the law verbally. But when other bibliometricians, they started the graphical formulation presentation of the law, they found there is an ambiguity. This ambiguity has been expressed here. That is, Bradford expressed his law in two different ways, graphically and verbally, resulting in two different formulations. One is verbal formulation, that is Nm is to Nm minus N to m minus Nm is to N3m minus N2m, that is 1 is to Am is to Am square. Here Am means Bradford multiplier, Nm means number of journals contributing n number of papers, that is the cumulative total. Now if we take in the verbal formulation, we take first 10 journals, then 60 minus 10 journals, then 360 minus 60 journals, and we get the ratio 1:5:5 square. In the graphical formulation, it comes like that: Nm is to N2m is to N3m, that becomes 1 is to Bm is to Bm square. Bm is Bradford multiplier. Here we find 10 is to 60 to 326, that is 1 is to 6 is to 6 square. It is Bradford zip distribution. Many a time Bradford distribution is called Bradford zip distribution because part of the Bradfordian curve is like zip distribution, which becomes straight line. And Kandal, he also showed that taking a data set of Bradford distribution, he showed that Bradford data set and data produced by Gibbs law, they are to a large extent. This is one table, and this table indicates the Bradford distribution. It is a continuation of table 1 showing rank number 6 to 84 and cumulative total 76 to 237. This is a table. It is showing GIF distribution with Bradford data set. It is the continuation of the table showing rank number 10 to 84, and here also Rankine frequency has been given, and one can see the Rankine frequency, the variations are, that is, quite not very wide. Hello students, we have finished discussion on another module that was on Bradford distribution. In this particular module, we have seen some of the formulations like Lime-Quires formulations, Coley's formulation, Brooks formulation, and so on. Also, we have seen the various viewpoints like that of Naranans. Now, summing up, we can say that these all bibliographic distributions, they are expressible through algebraic expressions. All of them. We have seen Bradford, we have seen Lothkas, also we have seen GIFs. All these expressions, all these formulations, all these distributions are expressible through algebraic expressions. Now, they also can be presented through graphs, except the graph of Bradford's law, which is J-shaped. The other graphs, they take the form of the graph of power law distribution. So these distributions are well established and have found publication in numerous areas like journal selection, ranking of author, finding out the prolific authors, ranking of words for for keyword generation, and so on. The classical laws of bibliometry generally follows power law that we have already seen, and all these laws are basically different versions of a single bibliometric distribution. This apart, these bibliometric laws or the bibliometric distribution, they have given rise to several other areas of knowledge like Scientometrics, Informetrics, and now we are also having the area of viewpoint. Now the Informetrics, they are the part of, and of course bibliometrics play a role in all these. Viewpoint is again bibliometrics with data derived from the World Wide Web. Scientometrics, that is bibliometrics related to science, and when bibliometrics and informetrics, they are merged, we get Informetrics. In this way, this particular law has given rise to several disciplines. Maybe in future, more and more disciplines will come up basing this particular law, and there may be more formulations, there may be more remarks, and more studies on this. And I like to tell you here, students, that nowadays a very large number of PhD research work is being done on bibliometrics. If you go through the list of bibliography of researches conducted on library information science from India, you will find that about 10% or maybe around 10% of the researches, they are in some way or the other are connected with bibliometrics.